Hi, I'm Jared Vojtilovich, an automation engineer here with Minuteman Empire Automation Systems. Today, we're going to be doing another Asyril video, this time actually showing how to program a recipe. As a prerequisite, if you haven't already, please go watch the how to calibrate a camera with your Asycube itself via the I+ controller, as that step is crucial in establishing your pixel to millimeter ratio for the steps following in this video. So on my I+ software I have here on my laptop, I'm going to go to recipes and create a new recipe. We will further do some additional videos later on showing the multi-feeding and multi-model recipes, but for the sake of this video, we're going to stick with a single recipe. So as I mentioned before in the other video with the camera calibration, it's, really simple the way that Asyril goes through and shows you how to set up a part or a recipe. So we're just going to follow the steps that they recommend on my screen here. First thing I'm going to do is just change my recipe name to Thai blocks. And kind of as a little sneak peek, we're going to be using little zip tie blocks to perform this camera or the recipe creation here. So what it wants me to do is it wants me to make sure that I have the correct plate on my Asycube. I'm then going to fill roughly a third of the plate with parts. So if I can get all these ready to go, what I'm going to do is put the parts on my cube as shown, and then kind of spread them out in a random pattern, making sure that none of them are actually touching and that they're all relatively spread out. So I have this going here. And at this time, the orientation of the part isn't truly critical. We'll get into that in a little bit here. So, as per my instructions from Asyril, I have roughly a third of the plate filled, and I'm going to continue to the next step. So now on the image acquisition. So I have here set up a front light and my back light, which is red in this scenario for hour 240. So in the settings tab, there are a couple different ways that you can manipulate the quality of the images that are taken. So right now we have it set up so that for 20 milliseconds for both the backlight and the front light, the camera will take images at those exposure levels and give us essentially a list of images to work off of for the first step. So if I start the image acquisition, you'll see that the backlight will turn on and eventually the front light will turn on and work through those image sets. So as it's doing its thing here, it's collecting that set of data or those images for us to use for the following step. Okay, so it looks like it's done there. So after it's done processing, we get a completed prompt and we can continue on to the next step. So the first step that the system is going to try to do is a blob analysis. It wants to make sure that the collection of pixels that it sees matches a certain criteria as a candidate, whether that's a good candidate or a bad candidate. That's for us to decide in the following steps. However, these steps here are going to be for the blob analysis step. So I'm going to select my backlight, and I can switch between two different images here, a black and white image or the image that the camera is seeing itself. I like the black and white image. It just shows contrast in the contours of the part itself. So I know that the exposure time here is a bit high, so I like to work maybe around 7 or 8 seconds. And you can see on the screen here, I have these edge blobs, or really things that are just noise in the background. So what I can do is go to my advanced options and actually filter out the difference level. And what that'll do is it'll get rid of any of the pixels that vary in difference between the blobs that we actually see and the backplate. Additionally, because we did go ahead and do that camera calibration, we do know our pixel to millimeter ratio. So the system does know the relative area in terms of millimeters for each of these blobs. So if I did have some pesky blobs that weren't going away based off of my difference level, I can actually go in and filter that out based off of my noise filter area here. So it looks like my image here is pretty good. So I'm happy with this image. I'm going to continue to the candidate detection results. So what it's doing is it's looking to see if there are parts within my area bounds that match the criteria I set up. So between 136 and 205 millimeters squared, it's saying that anything within that range is a good candidate. You can see here we have a couple that look like they're touching, and I have an area of 344, which is roughly 140 millimeters larger squared than my upper bound. And again, those are touching, so I'm going to leave that as is. So I'm happy with those settings, and I'm going to continue to the next step. So the first step, as I mentioned, is blob analysis, and now we actually want to go in and do candidate selection. Is it a good candidate or a bad candidate? Now, if your part doesn't really land in a specific orientation, or if it doesn't land in an orientation that is critical for your picking application, you can go ahead and actually skip this, because you can say that, okay, all my parts are good. However, if there is a specific orientation you're looking for, you can really leverage the front light with the camera to detect details on your parts that tell you what orientation that part is actually in. So if I go through, I can actually change the acquisition settings that I use for each of the different steps. So when I go from blob analysis to my candidate selection, I can change those exposure settings and acquisition settings. So what I'm going to do, because I actually care about what side these parts are on, I'm going to change from my backlight to my front light. This allows me to actually go in and see the detail of the surface of the parts themselves. And for the purposes of this demonstration, I'm going to say any of the parts that do not have the numbers showing, essentially the prongs of the tie block are facing down, I'm going to say that those parts are considered bad, and then any of the ones that have the prongs facing up are considered good and will be considered pickable. So if I add this image, I will now switch from when I do my blob analysis using the backlight to my front light for candidate selection. So what it wants me to do is it wants me to get a collection of good parts and bad parts. So it wants 15 good and 15 bad, at least. With this being a learning software, the more data that you feed it, the better it will learn for future cycles or future productions as this thing is running. So what I'm going to do is take an image, and then I can flip the parts. So it wants at least 50 candidates. It's not considered 50 images. It wants, the candidates that we established are good candidates initially to begin with. Again, and take another image until I get those 50 candidates that it's looking for. So now I can actually go in and start the classification process. So what I'm going to do here, again, as I mentioned before, is anything that has the prongs facing up is going to be considered a good part, and anything that has the prongs facing down and those numbers are visible on the back side of the tie block is going to be considered bad. So all I'm going to do is click right or click left on the good candidates and bad candidates. So here we have good. There's our first bad candidate, a couple more. Essentially, it's just going through and classifying, what's good, what's bad, so the system has a database to learn off of when it's actually going through and making a decision on what's a good part and what's a bad part. And you can see here I actually messed up one of the parts, so it's as simple as going back, Xing it out, and it throws it back in the pile for you to make that decision, good or bad. So I'm going to say that this is a good part, and continue through, bad part. The system's really great. Again, with that 6.3 megapixel high resolution camera, you're really able to see some of those details that may be difficult for other vision systems to see when it's doing a process similar to this. So once we go through, and once we get the correct number of candidates it's looking for good and for bad, we can then continue with the process. So this says that there are enough candidates classified, so I can apply this classification for future steps. So as you can see on my left side here, I have a little bit of statistical data relating to what it sees as a good part or a bad part. And it's saying with, at a minimum 97.8% certainty, it's able to see that, I have good parts or bad parts. So I'm gonna actually bump my threshold up here to 90%. And then I can continue to the next step. So again, as I mentioned before, for each of the different steps, you're able to leverage if you want to use your front light or your back light. I'm going to switch back to my backlight just because it gives me better contrast to be able to see the contours of the part that it creates on the back plate. So if I continue the next step here, What I really want to do is locate this center circle here. So what I can actually do is come in and mask my part. I can close this out. And I really don't care about any of the outside features at the moment here. I'm really just trying to establish where my pick point is for my part. And what I can do is come in and grab the circle tool and align it to the best of my ability to that center contour. And bring these sides in here and there. And I'm going to say that's pretty good. Now all I have to do is click my targeting tool, and that will bring it right into the center of my circle that I created here. Now it's important to know that the part height established in this section is not necessarily the overall part height from the bottom of the plate. It's really where that contour is, that center circle, with respect to the base plate. So the reason that that's critical is because there's a phenomenon called parallax, where if the part is not exactly on the center line of the camera, there's going to be a little bit of distortion going on with what the camera sees and what the part actually is and where it actually is on the plate. So entering the part height in here, which I know is roughly 4 millimeters, so that hole, the features, the contours of that hole are 4 millimeters off of my plate. And that's going to allow for the system to correct for that parallax effect. So the next thing I'm going to do is go to my pick point teaching results. So the steps that we've worked through so far are the blob analysis, candidate selection, and now we have a pick point analysis as well. So I can see that at a minimum, with 99.9% match to the contour that I just created, I am able to identify the pick point on each of these good candidates. So I'm going to bump my threshold up to, let's say, 90%. You can see none of them drop out. And then I can actually go in and teach my pick angle positioning. Again, as I mentioned, when you work through these, you're able to switch the acquisition settings. Again, I'm going to leave them using the backlight. However, if there were features that defined which angle your part needed to be picked at, you could leverage the front light in that scenario to be able to identify that feature on the part to establish your pick angle. So now I can come in and I can create another mask if I wanted to. So in this scenario, I don't really care about my center circle. I more care about the long edges and short edges and where those are. So I'm going to come in, I'm going to actually mask out a lot of the details in here. So my center circle, I don't care about. I really care about, let's say, where these shorter edges are. So I can actually come in and mask out my long edges and create a contour that the system's going to try to match for each of these different parts. So because the pick point is on the center, I can now establish which orientation I want my part to be picked in. So I'm going to say that my X perpendicular to my long edge is the orientation I want my part to be picked in. However, the overall orientation doesn't matter which long edge I pick off of. So what I can do is I can come over and check my part can be picked from multiple angles, and you can pick up to 20 different angles, as you can see here, for the part orientation. So because I want my X to be perpendicular to either of the long edges, I'm going to say that I can pick my part from 2 different orientations or 2 different angles. So now I can actually go into my pick angle results. And as you can see, the x-axis for each of the good candidates is perpendicular to the long edge of all the parts that are considered pickable up to this point. And again, with up to 99.9% match on the contour that I created for my mask, I am able to identify my pick angle for each of those parts. So I'm going to bump this up to 90%. So the next thing I can do is go to my pick conditions. So this is where we're going to set up how our part is going to be gripped and the gripper geometry relating to the gripper or end effector that we're actually using. So if I know that my total stroke on my part, or on my gripper per se, is roughly 20 millimeters, I can come in and establish a stroke, an open stroke of 20 millimeters, roughly somewhere around there. I can say that my fingers are roughly, we'll call it 7 millimeters. So if I get really close to 7 millimeters, I can overlay my gripper geometry onto the part. And now what it's going to do is, for each of my candidates that have passed the criteria, again, blob analysis, pick point, candidate selection, and pick angle, it's going to overlay this geometry on there and check to see if the gripper is going to potentially collide with any other parts. So once I have that established, that's good. If you were to use vacuum to pick any parts, you would use the circular tool. But because we're going to hypothetically say we're using a mechanical gripper, we're going to overlay rectangular shape. So now I can go to my picking limits. So this step is also critical too. So if you are using a mechanical gripper, you want to make sure that when your gripper is in the open position and it approaches a part, you want to make sure that that geometry does not collide with the boundary of your plate as well. So what you want to do is make sure that your boundaries here are in far enough such that your gripper geometry does not collide with the plate. And this will take into account when it determines what parts are pickable for both the collision geometries, so that overlay, as well as whether or not the gripper is going to collide with the sidewalls as well. So we can see that here in our final, we'll call it a check. So up to this point, we've done blob analysis, candidate selection, pick point teaching, pick angle teaching, and then our gripper geometry and picking conditions. So the culmination of all of those give us this screen here, which shows, candidates that are pickable and those that are not. So as you can see, we have parts that are on the incorrect side are considered candidates, but they are not considered potential pick candidates because they are in the wrong orientation. Here, again, because those parts look like they're touching, this whole thing looks like a single blob. It's outside of our blob boundaries, so therefore it is not even considered for pick. And you can see the respective geometry and data that the system is seeing. So these values here are technically in the camera coordinates. They are not yet in the robot coordinates. That will be in a future video showing how the system calibrates itself to the robot's coordinates. But for the purposes of this video, the coordinates that you see here are going to be with respect to the camera coordinates. So now we can come into the Asycube configuration. We're going to actually go in and manipulate the parts so that they behave the way we want them to. So what I want to do really is push the parts from the one side and make sure that the parts are able to make it from one side to the next. And how long does that actually take? So I know I'm going from my pin to the opposite side. So if I select on the screen here, right to left, I'm going to select that vibration, and I'm going to just really test, with the default values, how the system reacts to pushing the parts from one side to the next. So with 3 seconds at an amplitude of 65 and a frequency of 65, I'm going to see how they react. So it looks like all the parts actually made it over with the default values. So I'm going to make sure that the values for the left to right vibration are the same, which they are. We have 3 seconds, we have 65 on the amplitude and 65 on the frequency. I'm going to make sure that my parts behave the same way, going from, in this case, top to bottom. So if I have my vibration here, it looks like they're struggling a little bit to get to the other side. So what I might do is I might bump up my amplitude here from 80 to maybe 90 and test the vibration again. Maybe we'll go even up to 100. And the reason that this is critical, we'll get to that here in a second. Let's say a majority of them made them majority of the way over to the other side. So what I'll do is I'll copy those settings as well from the top to the bottom to the bottom to the top. And then I will go 100% on the amplitude there. Testing a flip vibration, so I just want to make sure that those are able to flip the side. Looks like they're behaving properly. So we can continue to the next step. So this is going to be hopper tuning. So again, we are using the new Asyril hopper here. We have the 1 liter option, and that takes an analog input from the hopper. So I want to switch to analog output. So I'm putting that out from the hopper from the cube into the hopper itself. So what I want to do is I want to figure out, okay, how many parts do I want on my plate optimally? Like, what's my fill percentage? So I can say that, at all times I want to make sure that I have 20 parts on my plate. And for the sake of this video, we'll say that it takes 1 second to actually get that number of parts onto my plate. So what happens here is it looks to see how many parts are actually on the plate itself. So, for round numbers, I'm actually going to change this to 10. So let's say that I wanted to make sure that I had 10 parts on my plate at all times. So if after a couple cycles of picking, the robot's coming in, picking the part, doing the operation that it's doing on the side, the system sees that, okay, I've picked 4 parts, therefore I have 6 parts left on my plate. Well, I know that it takes 1 second to get the optimal number of 10 parts onto my plate, and now I need 4 more parts. So what it's going to do, it's going to vibrate over a proportional amount of time, so 400 milliseconds, to get those 4 additional parts. And with the new Asycube system, as the hopper empties the parts, the hopper, at least the payload that's on the hopper itself, becomes lighter. The hopper will automatically adjust the amplitude and frequency of that vibration to get that number of parts onto the plate. So it's a really neat feature that we see there. So now we come into the actual vibration profile, or the vibration sequence. So the reason we went through before and actually set up the timing for how long it took for the parts to go from one side to the next and then a flip operation really deals with this, right? So we have a smart fill operation here. So again, that's going to get the optimal number of parts to our plate, but then we want to manipulate those parts to get them as close to the center as possible when we start. So what the system does is it looks at the center of mass of pixels, where they are on the cube themselves, and then automatically adjusts the vibration to get that center of mass to the center of the plate. And the way that it does that is if it knows that it takes 2 seconds to go from my full left side to my full right side, then I know that it takes 1 second to go from my full left side to the center, and I know that it takes half a second to go a quarter of the way. So what it does is it proportionally vibrates the coils to be able to manipulate that, and it knows how much it needs to vibrate each coil to get the center of mass of those pixels roughly to the center of my plate. It then performs a flip operation, which is seen here, and I can actually make that a little bit longer so we can see it on the settings there. So we have a flip operation for 400 milliseconds, and then it's going to wait 500 milliseconds to make sure that the parts are all settled before I actually take my image. So to test that, what I'm going to do is I'm going to move my parts off to one side of the plate, and what you'll see is a large orange circle with crosshairs, and that's the center of mass of pixels on the plate. You'll see where it is before, how many pickable, how many are rejected, and then it will go through the vibration sequence. You'll see that center of mass move as close to the center as possible, and then it will perform another vision operation, and you will see the center of mass change. So as you can see here, the center of mass was all the way to the right, because that's where I placed them. I had 0 pickable parts and 0 rejected parts. Again, because all of these is just, it's seeing the system as one clump of pixels. It's not identifying any of those as potential pickables. And then it moved the center of mass from right to roughly center of my plate. And now I have 9 pickable parts and 6 rejected parts. And if I run through that sequence again, you can see I now have 5 pickable, 9 rejected. Again, this part here is on its side. It's not passing the blob analysis. These two may look like they're touching, not passing the blob analysis. Same with these two. Now, if I take some of these parts off of my plate, we can actually see the hopper go through and do its thing. And if I run a sequence again, and there's that. And then if I run it one more time, we have the hopper vibrating there and waiting. So when I finish and close my recipe, there are a couple important things to know. If you are using one of those plugins from one of those large robot manufacturers, you would use this recipe ID, not necessarily the recipe name, when you actually go through and set up your program and the associated functions with that plugin. So this is how you go through and you program a recipe. It gets a lot simpler when you do it a couple times. For the purposes of this demonstration, I walked through and kind of voiced over how to do these, but the system and the procedures that you use to actually go through and program the recipe. It gets much simpler as you do them. So I hope this has been informational. And again, click the link in the description. Remember to subscribe for more Asyril related videos, as well as other products and technologies that Minuteman Empire Automation Systems supports. Thank you.